Welcome to lecture 7, continuous views, a sharp rise of impressions, and subscribers motivate me to compile and complete all lectures. Thank you all. Usually, these are not only a combination of thermal and mechanical properties. It will explain the refractory sustainability and how to fix specifications when both temperature and load are employed together during application. So, let us discuss thermomechanical properties for refractories. Let us start by explaining the difference between individual thermal and mechanical with thermomechanical properties. All individual thermal and mechanical properties cannot confirm the high temperature refractory behavior in operation. Thus, a few common questions are obvious. What will be the maximum temperature sustainability without deformation under constant load? When will the refractory collapse under a continuous load at a predefined temperature? What will be the bending, compressive and tension combined behavior at high temperature to accommodate stress? To know all the above three, we have to perform refractoriness under load, creep in compression and hot modulus of rupture respectively. We can take this image as a reference where low impurity indicates high PC, that is pyrometric cone equivalent, and different thermal and mechanical properties may indicate the acceptability of this refractory, but these are not enough. We have to evaluate thermomechanical behavior that helps to simulate the real life application while both are employed together. Thus, thermomechanical properties are determined using high temperature test methods that external forces causing stresses on the tested material. Stress strain behavior of refractories at high temperatures is very complicated because reversible elastic strain and non-reversible non-elastic time dependent deformations occur. Therefore, the thermomechanical behavior of refractories must be considered as the interaction of four variables: stress, strain, temperature and time. Before judicious refractory selection, it is essential to remember that refractory material is required to maintain dimensional stability under extreme temperatures, including repeated thermal cycling, massive mechanical load and constant corrosion from hot liquid and gases during application. We can start our discussion with a couple of developmental works that eventually help understand the importance of thermomechanical response and sustainability during high temperature applications. In this work, first pyrometric cone equivalent of high alumina refractory was determined by standard cone. This is the developed material, and estimated the sustainable temperature without load is T1, that is 1750 degrees centigrade. But this is not enough, while refractory has to withstand high temperature and load together. Thus, two questions: at constant load, at what temperature will it sustain, and how long will this refractory sustain at a definite temperature with a continuous load? To answer first question, it is essential to execute RE well, where 0.2 Newton per millimeter square load was employed on 50 millimeter dia and 50 millimeter height cylindrical specimen and deformed at T2, usually 150 to 200 degree centigrade less than the T1 temperature. Silica brick is exceptional. Usually, this deformation or damage follows either buckling, barreling. This is one typical schematic of barreling, or shearing fracture, or combination of all above, depending on the refractory composition and in situ phase formation. Further, that can be confirmed after taking XRD and FEACM of cross section of the deformed specimen. But it cannot explain how long it will sustain at T2 and employed load. To overcome, need to execute creep. Usually creep in compression is done at T3 below 100 to 150 degrees centigrade of T2, that is deformed RE well temperature. Typical creep behavior of metal under tension is shown in figure, where 3 stages of strain time are observed, in which steady state or secondary creep is the most important zone of interest to understand the creep rate. The expansion behavior under tension increases with temperature and stresses. Some failure mechanism has been represented by schematic of metal under tension. Usually, RUL and creep are important thermomechanical behavior for alumina, magnesite, macrome and silica defined oxide refractories. Whether HMOR characterization as a thermomechanical response is common practice for carbon based refractories. We can discuss on magnesia carbon brick for slag zone timing ladle. A common user end statement to refractory manufacturer is, may you please enhance the hot modulus of rupture of magnesia carbon for slag zone for better performance and life. Obvious, there are solutions and scope to enhance HMOR, that is bending strength at high temperature, but why a high HMOR value is required when the entire lining experiences compressive load only? Is high always good? What is the basis to select HMOR testing temperature? With consideration of this image and this statement, low strain refractory cannot accommodate high stress, that is thermomechanical stress towards circular backup lining in operation, we can solve and explain all, and more further will be discussed later. Here we will discuss RUL, what is happening and how it is evaluating. The temperature at which material softens indicates refractoriness is represented by PC, pyrometric cone equivalent, usually higher than the application temperature and RUL. Silica has near to equal PC and RUL. Refractoriness under load is a function of deformation behavior of ceramic refractory products that are subject to increasing temperature with constant load, eventually collapse of refractories. So, this is the basic difference between the PC and RUL. RUL is more crucial than PC while designing refractory composition. A typical RUL testing setup for refractory specimen is given. This one, this is the load, this is the specimen from here viewpoint pyrometer. Typical RUL characteristics of alumina refractory specimen is initiate deformed 0.5%, beyond 1400 degree centigrade completely collapse or breaks at 1480. Safer surface temperature in a particular situation is essential. During the experiment, it measures softening temperature as refractory is a composite material, not we are measuring the fusion point. What important parameters are essential to consider to design high RUL refractories? Certain philosophies are important to consider during design or to achieve high RUL. Minimization of formation of glass phase under load and temperature, particle packing to reduce the porosity, high compressive strength of starting raw materials grains, that means without any micro crack of the grains, and high density of the grains. However, contributing factors to the increased resistance of bricks under load during application are more thorough distribution of liquid phase rather than localized accumulation. That means it is quite obvious when the phase is forming, and if the viscosity of the phase is low, the possibility of deformation more. The growth of crystals through the influence of heat, crystallization of a portion of the liquid during cooling. A competitive deformation temperature of several oxide refractories during RUL testing has been given in the figure. Simultaneously, relevant regions are pointed out. For example, fire clay brick containing relatively high impurities refractory has less RUL deformation temperature than sillimanite brick. RUL is essential to select proper composition for designing of oxide refractories, and it is different from creep. In obvious, the mode of creep measurement is different from RUL. In creep, the percent of shrinkage of refractory specimen under a continuous load and exposed to a constant high temperature over a long period is determined. A typical creep behavior at 1400 degrees centigrade exhibits the creep rate and final failure time at a load of 100 Newton with a rate of 0.3 millimeter per minute. This is thermal expansion behavior may superimpose during the initial creep stage, and it is difficult to explain such behavior. Here two fundamental creep mechanisms have been given: Navarro herring creep through lattice diffusion within, Covell creep through diffusion at grain boundaries, that is through grain boundary. At low temperature, the activation energy for grain boundary diffusion is less than that for diffusion through grains, that is Covell creep is much more predominant and less activation energy required. A characteristic creep behavior at 1500 degrees centigrade of different oxide refractories is shown in the figure. While comparing alumina 60% and corundum 95% bricks, the secondary phase and impurity content reduce the creep resistance. Similarly, low iron containing magnesia exhibits high creep resistance. Raw material and process design are important phenomena to achieve an optimum dense refractory for a particular application. Thus, it is more suitable for characterizing the creep behavior of material under service conditions, evaluating the effect of stress level and temperature on creep, and determining creep strain and rupture strain. Here the testing mode is almost similar to CMR, that is cold modulus of rupture, but the sample must be placed in a furnace heated to a predefined temperature and broken with a plunger as shown in the figure. This test facilitates to know the following: resistance to thermomechanical stresses generated during heating and cooling of the refractory lining in a ladle, the bonding strength between the matrix and the grains in the refractory body. It is influenced by the amount of liquid generated at the most temperature, preferentially at the test temperature, viscosity, microstructure consisting of different porosity, microcracks, etc., and their distribution in the refractory body. How does fracture happens and switch to plastic deformation during high temperature bending? The load displacement plot for refractory differs from high temperature bending of fine grained ceramics like this. High temperature in situ formation of the secondary phase enhances the plastic deformation. It may be the whisker phase like aluminum carbide, low viscous phase or other phases. A high content of low viscous phase facilitates rapid slag interaction, thus pore formation and slag penetration, or volume expansion like spinel phase may enhance micro cracking. Despite these micro cracks always exist in refractory bodies with coarse grains that compile and extend the crack. In Abhyas, the strength of refractory depends on the dimension of the critical crank length C and follows this equation, that is the KIC is the fracture toughness. High fracture toughness is less prone to fracture and more strength. A typical crack propagation beyond critical crack length and their dissipation have been shown in the animated figure. This. In the last slide, we want to touch on our recent work, thermal shock resistance of nano reinforced alumina magnesia carbon refractories. More details are available here. Thank you for your time and attention. I hope you found this lecture informative and thought provoking. I wish you all the best in your future endeavors. Please get in touch with me for further explanations if required. Encountering with your knowledge and interest in the next lecture. Have a nice time ahead. Thank you. Thank you for your patience.